For centuries, humans have looked up at the night sky and wondered, are we alone in the universe? Among all the celestial bodies that fill our cosmic neighborhood, one planet has stood out as a tantalizing candidate in the search for extraterrestrial life: Mars. The idea of life on Mars has captivated scientists and dreamers alike. From ancient civilizations observing the red planet with the naked eye, to modern-day robotic explorers roaming its dusty surface, the search for Martian life is more than just a scientific pursuit. It's a quest to understand our place in the cosmos. If life once existed on Mars, or perhaps still lingers in hidden pockets beneath its surface, it could revolutionize our understanding of biology, evolution, and even our own origins. This search falls under the realm of astrobiology, an interdisciplinary field that seeks to understand the conditions necessary for life beyond Earth. Through robotic missions, satellite observations, and ambitious plans for future exploration, astrobiologists are tirelessly working to uncover Mars' deepest secrets. Their efforts are driven by a fundamental question: what makes a planet habitable? And could Mars have ever met those conditions? Despite its barren, inhospitable landscape today, evidence suggests that Mars was once a very different world. A planet with liquid water, a thicker atmosphere, and perhaps even the right chemical ingredients to support life. In this video, we'll take a comprehensive journey through the search for life on Mars. We'll explore the historical efforts, examine current missions, delve into potential Martian habitats, and look ahead to the future of exploration. Could Mars be home to microbial life? And if so, what does that mean for humanity? Stay with us as we unravel one of the greatest mysteries of all time. Mars has long held a special place in humanity's imagination, often depicted as a world teeming with alien civilizations, or, at the very least, a planet harboring the remnants of life. In the late 19th century, astronomers like Giovanni Schiaparelli and Percival Lowell fueled speculation with their observations of so-called canals on Mars, which they believed were evidence of an intelligent Martian race struggling to survive on a dying planet. Though these theories were later debunked, the fascination with Mars never faded. By the mid-20th century, as space exploration advanced, Mars emerged as the prime target in the search for extraterrestrial life, not because of fictional Martians, but because of its striking similarities to early Earth. Scientists realized that if life ever arose elsewhere in the solar system, Mars was one of the most likely places it could have happened. The strongest argument for Mars's potential to have once supported life lies in its ancient past. Billions of years ago, Mars was not the cold, desolate world we see today. Geological evidence gathered by orbiters and rovers suggests that early Mars had conditions far more hospitable than its present state. Scientists have identified vast networks of dried-up riverbeds, lake basins, and even signs of an ancient ocean that may have once covered much of the planet's northern hemisphere. These findings indicate that Mars was once warmer and had a thicker atmosphere, allowing liquid water to flow across its surface. However, over time, the planet lost much of its atmosphere, possibly due to the weakening of its magnetic field, which left it vulnerable to solar wind stripping away its protective gases. As the air thinned, temperatures dropped, and liquid water either evaporated into space or became locked away in underground reservoirs and polar ice caps. Despite these dramatic changes, Mars may still possess the key ingredient for life: water. Though surface conditions are harsh, with extreme cold and radiation exposure, recent discoveries suggest that water persists beneath the surface in the form of vast ice deposits. Radar scans from orbiters have detected thick layers of water, ice buried beneath the Martian soil, And some studies propose that seasonal temperature fluctuations could cause periodic melting, forming small pools of briny liquid water. This is especially exciting because, on Earth, microbial life has been found thriving in some of the most extreme environments, including subglacial lakes in Antarctica. A 2018 NASA study even proposed that Martian microbes, if they exist, might survive beneath frozen water, shielded from radiation and sustained by chemical nutrients trapped in the ice. These possibilities make Mars one of the most promising locations to search for alien life, past or present, and fuel the ongoing efforts to explore its surface and subsurface for definitive signs of biological activity. Defining life may seem straightforward, but when searching for it beyond Earth, scientists face a significant challenge. What exactly qualifies as alive? On Earth, life takes an astonishing variety of forms, from microscopic bacteria to towering redwood trees, yet all living things share certain fundamental characteristics. However, when considering the possibility of alien life, especially in environments vastly different from our own, rigid definitions can become problematic. Could there be life that doesn't conform to our expectations? Could an organism exist without some of the traits we associate with life? These uncertainties make it difficult to establish a universal definition. Instead, scientists focus on identifying key characteristics that all known life forms exhibit, using these as a guide in the search for extraterrestrial organisms. At its core, life is an active, dynamic process. Living organisms must be able to store and use energy to sustain themselves, whether through photosynthesis, consuming organic material, or extracting energy from chemical reactions. They must also grow and, in most cases, reproduce, though some organisms, like certain bacteria, can remain dormant for extended periods. Another essential trait is the ability to respond to the environment, adjusting to changes in temperature, radiation, or nutrient availability. Lastly, all life must have the capacity to evolve and adapt over time, allowing species to persist despite shifting conditions. These characteristics form the foundation of how astrobiologists approach the search for life on Mars, looking for biological processes that mirror those on Earth while remaining open to unexpected possibilities. In addition to these defining traits, life as we know it requires several key ingredients. The most critical of these is liquid water, as it serves as a solvent for biochemical reactions and facilitates the transport of nutrients. This is why the presence of water, past or present, is often the first indicator of a potentially habitable environment. Beyond water, an energy source is essential, whether from sunlight, as in photosynthetic organisms, or from chemical reactions like deep-sea vent microbes on Earth. Nutrients, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are also necessary to build the molecular structures of life. Lastly, life needs protection from harsh environmental conditions. On Earth, our atmosphere and magnetic field provide shielding from radiation and extreme temperature fluctuations, but on Mars, any surviving organisms would likely need to be underground, hidden beneath layers of ice or rock to avoid harmful solar radiation. These criteria help shape Mars exploration missions, guiding scientists as they search for environments where these conditions may still exist. If life once thrived on Mars, or if it lingers in isolated pockets today, it must have found a way to meet these fundamental requirements. Mars presents an environment that is both unforgiving and intriguing. Unlike Earth, which boasts a thick, life-sustaining atmosphere, Mars has an incredibly thin one, composed mostly of carbon dioxide with only trace amounts of oxygen and nitrogen. This lack of atmospheric pressure means that liquid water on the surface quickly evaporates or freezes, making it nearly impossible for life as we know it to thrive in the open. Compounding this challenge, Mars is an icy desert, with average temperatures plummeting to around -80 degrees Fahrenheit, -62 degrees Celsius. And at the poles, conditions can be even more extreme. Any life that might exist today would have to endure these freezing conditions or find refuge in more stable environments. Another major hurdle is radiation. Without a strong magnetic field to shield it, Mars is bombarded by cosmic rays and solar radiation, levels of which would be lethal to most known Earth-based organisms. This presents a significant obstacle for both microbial life and future human explorers. However, even in such an inhospitable world, there are pockets of opportunity where life could find a way to survive. Scientists believe that one of the most promising locations is beneath the planet's surface, where ice deposits could periodically melt to form liquid water. Intriguingly, dust mixed within the ice may absorb sunlight, creating a greenhouse effect that melts the surrounding ice from within. This process could lead to the formation of tiny, temporary pockets of liquid water, potential refuges for microbial life. Beyond these icy reservoirs, some researchers speculate that Mars may still harbor underground aquifers or even small lakes beneath its southern polar ice cap. In 2018, radar data from the European Space Agency's Mars Express orbiter suggested the presence of a liquid water lake beneath the ice, a discovery that, if confirmed, would have profound implications for the planet's habitability. Additionally, there's the possibility that Mars once hosted hydrothermal systems, regions where heat from the planet's interior warmed underground water, much like the hydrothermal vents found on Earth's ocean floor. Such environments on Earth are known to sustain rich microbial ecosystems, raising the question, could similar conditions on Mars, either past or present, have provided a foothold for life? These potential habitats continue to drive scientific exploration, offering hope that the red planet might still harbor secrets waiting to be uncovered. The exploration of Mars has been a long and evolving journey, beginning with the earliest attempts to unravel its mysteries. The first successful missions to the red planet were NASA's Mariner spacecraft in the 1960s and 70s. Mariner 4 was the first to fly by Mars in 1965, sending back the first close-up images of its cratered, desolate surface, shattering hopes of finding a lush, Earth-like world. Later missions, Mariner 9 and the Viking program, provided even more detailed insights. Viking 1 and 2, which landed on Mars in 1976, conducted the first direct search for microbial life. Their onboard experiments analyzed Martian soil for signs of biological activity, but returned inconclusive results. While they found no definitive evidence of life, they did confirm that Mars had a history of water activity, reinforcing the idea that the planet might have been habitable in the past. In the early 2000s, the Mars exploration rovers, Spirit and Opportunity, revolutionized our understanding of the planet's history. These twin rovers, designed for 90-day missions, ended up lasting years. Opportunity operated for nearly 15 years before its mission ended in 2019. Their discoveries provided compelling evidence that Mars was once much wetter. Opportunity, in particular, found mineral deposits like hematite and gypsum, which form in the presence of water, suggesting that its landing site, Meridiani Planum, was once home to a shallow, salty sea. Spirit, exploring a different region, found evidence of past hot springs and volcanic activity, environments that on Earth are often teeming with microbial life. Building on these discoveries, NASA's Curiosity rover, which landed in Gale Crater in 2012, took the search a step further by investigating whether Mars ever had conditions suitable for life. Curiosity's instruments confirmed that Gale Crater was once a long-lived lake, with fresh water that could have supported microbial life. It also detected organic molecules, complex carbon-based compounds that are essential building blocks of life, suggesting that Mars once had not only water, but also the necessary chemistry for life to emerge. Currently, NASA's Perseverance rover, which landed in Jezero crater in 2021, is pushing the search even further. Jezero was once home to a river delta and a vast lake, making it one of the most promising locations for finding ancient biosignatures, fossilized evidence of past microbial life. Perseverance is not only analyzing the rocks and sediments for such clues, but is also collecting samples that will be stored for a future mission to bring back to Earth. This marks a historic step in Martian exploration, as scientists will be able to study Martian soil and rock in laboratories with the most advanced technology available. Each of these missions has brought us closer to answering the age-old question, did life ever exist on Mars? And, with ongoing exploration, we may be on the verge of finding out. Searching for life on Mars requires more than just looking for something that moves. It demands identifying biosignatures, the telltale signs that life once existed or may still persist. A biosignature is any feature, substance, or pattern that could have resulted from biological activity rather than purely geological or chemical processes. These can take many forms, from fossilized microscopic structures to chemical traces left behind in ancient rocks. However, detecting these signatures is no simple task, as the line between biological and non-biological processes can sometimes be blurred. One key category of biosignatures is morphological evidence, which includes fossilized microbial cells, layered sedimentary formations like stromatolites, which on Earth are formed by microbial colonies, or other microscopic structures that hint at biological origins. If Mars once had life, ancient rock formations in dried-up lake beds and river deltas might preserve these traces, much like Earth's oldest fossils. Another type of biosignature is elemental evidence, where scientists look for unusual concentrations of certain elements, such as carbon, nitrogen, and sulfur, in patterns that suggest biological activity. For example, life on Earth, preferentially, uses lighter isotopes of carbon, leaving behind a distinct chemical signature in rocks. If similar patterns are found on Mars, they could indicate past microbial life. A more direct biosignature is molecular evidence, such as organic compounds, carbon-based molecules that form the foundation of life. On Earth, all known life relies on molecules like DNA, RNA, amino acids, and lipids. While scientists don't expect to find intact DNA strands on Mars, the presence of simpler organic molecules, especially in specific geological contexts like ancient lake deposits, would be highly intriguing. Curiosity has already detected complex organic compounds in Martian rocks, raising the possibility that Mars had the necessary ingredients for life. However, identifying biosignatures comes with significant challenges. One of the biggest obstacles is false positives, where non-living processes create features that mimic biological ones. For example, certain chemical reactions can produce organic molecules without any involvement of life, making it difficult to determine whether a discovery truly points to past biology. Another concern is contamination. Earth-based microbes can hitch a ride on spacecraft, potentially confusing results if scientists mistake them for native Martian organisms. Strict planetary protection protocols are in place to minimize this risk, but no system is foolproof. Finally, even if life once existed on Mars, its biosignatures may have been degraded over time by harsh radiation, oxidation, and geological processes. Unlike Earth, which has an active tectonic cycle that buries and preserves ancient fossils, Mars lacks this protection, meaning biological traces could be extremely faint or heavily altered. Despite these difficulties, scientists remain hopeful. By using sophisticated instruments and carefully selecting exploration sites, Missions like Perseverance aim to detect these elusive clues. If we do find definitive biosignatures on Mars, it would be one of the most profound discoveries in human history, proving that life is not unique to Earth and that the universe may be teeming with possibilities. One of the most exciting approaches to the search for life on Mars comes from studying some of Earth's most extreme survivors, extremophiles. These are organisms that thrive in conditions once thought to be completely uninhabitable, from scorching volcanic vents to the icy depths of Antarctica. Extremophiles push the boundaries of what we consider habitable, and their existence has reshaped our understanding of where life can persist. In the field of astrobiology, these organisms serve as living examples of how life might survive in alien environments, including the harsh conditions of Mars. Among the most intriguing extremophils are methanogens, microorganisms that produce methane as a byproduct of their metabolism. On Earth, they live in oxygen-free environments, such as deep underground, within ice, or even inside the guts of animals. The discovery of methane in the Martian atmosphere, detected in fluctuating bursts, has raised speculation that similar microbes might exist beneath the planet's surface, generating the gas through biological processes. Another relevant group is psychrophiles, organisms that thrive in extreme cold. These microbes have been found deep beneath Antarctic ice sheets, where they remain active despite freezing temperatures. If Mars harbors liquid water beneath its surface, even in small, briny pockets, similar life forms could potentially survive there. Likewise, halophiles, which flourish in highly saline environments like Earth's salt flats and deep-sea brines, are of great interest. Since Mars is rich in salts, and any liquid water on its surface would likely be briny, halophiles offer valuable insight into how Martian microbes, if they exist, might cope with extreme salinity. To better understand how life could survive on Mars, scientists study terrestrial analog environments, places on Earth that resemble conditions on the Red Planet. Deep-sea hydrothermal vents, for instance, are home to entire ecosystems that rely on chemical energy rather than sunlight. If Mars once had hydrothermal activity, similar subsurface ecosystems could have existed. Subglacial lakes, such as Antarctica's Lake Vostok, are isolated bodies of liquid water buried beneath thick ice, yet they host microbial life. These environments closely resemble the hypothesized underground water reservoirs on Mars, suggesting that life could persist in Martian ice. Finally, hypersaline, oxygen-deprived deep-sea basins, like the ones found in the Mediterranean, demonstrate that life can endure in extreme chemical conditions, conditions that might parallel ancient Martian lakes. By studying extremophiles, scientists gain valuable clues about how organisms might survive on Mars, what biosignatures to look for, and where to search for life. If life has ever existed on the Red Planet, it may not have needed Earth-like conditions. It may have simply adapted to the challenges of its environment, just as extremophiles do here on Earth. These hardy microbes remind us that life is resilient, and, perhaps, far more common in the universe than we once imagined. One of the most intriguing mysteries in the search for life on Mars is the detection of methane in its atmosphere. On Earth, methane is often associated with biological activity, produced by living organisms ranging from microbes to large animals. Its presence on Mars has led to tantalizing speculation. Could it be a sign of life? The mystery deepened when scientists discovered that Martian methane levels fluctuate, sometimes appearing in sudden bursts before disappearing again. NASA's Curiosity rover first detected methane spikes in Gale Crater, and orbiters such as the ESA's Mars Express and the ExoMars Trace Gas Orbiter have reported varying methane concentrations across the planet. However, the source of this methane remains unknown, and its intermittent nature has made it difficult to study. There are two primary ways methane could be produced on Mars: biological and geological processes. If methane is being created by living organisms, the most likely culprits would be methanogens, a type of microbe that survives in oxygen-deprived environments by breaking down simple molecules and releasing methane as a byproduct. On Earth, methanogens thrive in deep underground environments, beneath glaciers, and even in deep-sea hydrothermal vents. If Mars has subsurface water, especially in regions like Acidalia planitia, where conditions might be favorable for microbial life, methanogens could exist beneath the surface, releasing methane that occasionally seeps into the atmosphere. However, methane can also be produced through geological processes, without any involvement of life. One possibility is volcanic activity, though Mars does not currently have active volcanoes. Another leading hypothesis is serpentinization, a process in which water reacts with certain types of rocks, releasing hydrogen that can combine with carbon to form methane. This reaction has been observed on Earth in environments deep underground and in oceanic crusts, and it could be occurring beneath the Martian surface as well. Interpreting the methane detections on Mars is an enormous challenge. First, scientists must rule out non-biological sources to determine whether the methane is truly a biosignature. Even if it were produced biologically in the past, it could have been trapped underground for millions of years and only now be escaping, meaning it wouldn't necessarily indicate present-day life. Another major difficulty is pinpointing the source of the methane. Because Mars has a thin atmosphere and lacks strong winds to distribute gases evenly, methane can break down quickly due to sunlight and chemical reactions, making it difficult to track its origin. Some instruments have detected methane in specific locations, while others have found none, leading to conflicting results. Despite these challenges, the presence of methane remains one of the strongest clues that Mars might not be a dead world. Future missions will focus on detecting methane at finer scales, tracing its origins and determining whether it is a product of life or merely a quirk of Martian geology. If we can unravel this mystery, it could bring us one step closer to answering the ultimate question: is there, or has there ever been, life on Mars? As humanity advances in its quest to find life beyond Earth, the ethical considerations surrounding the exploration of Mars become increasingly important. One of the most pressing concerns is planetary protection, the effort to prevent Earth-based microbes from contaminating Mars. Every spacecraft that lands on the red planet carries a risk of introducing bacteria, fungi, or other microscopic life that hitched a ride from Earth. If such contamination were to occur, it could not only interfere with our ability to detect genuine Martian life, but could also pose a threat to any native organisms that might exist. To mitigate this risk, strict sterilization protocols are followed for Mars-bound missions, ensuring that rovers and landers are as free from biological contaminants as possible. However, as we move toward human exploration of Mars, maintaining this level of cleanliness will become far more difficult. Beyond contamination, the potential discovery of life on Mars raises profound ethical questions. If we find microbial life, should we leave Mars untouched to preserve it, or should we proceed with exploration and, eventually, colonization? Some argue that altering Mars to make it more habitable, through terraforming or other means, would be a natural extension of human progress. Transforming Mars could provide a second home for humanity, ensuring our survival beyond Earth. However, others contend that if life exists on Mars, no matter how simple, it has intrinsic value and a right to exist undisturbed. Introducing Earth-based organisms or altering the Martian environment could lead to the extinction of native life before we even have a chance to fully understand it. This debate extends to the broader issue of balancing scientific exploration with environmental protection. Just as we now recognize the importance of preserving Earth's ecosystems, should we also take a conservationist approach to Mars? Some scientists propose designating certain regions of Mars as biological preserves, where no human interference is allowed, while permitting controlled exploration in other areas. Others argue that ethical responsibility should go even further. If Mars has life, we should not only avoid harming it, but also work to protect and study it as a unique example of biology beyond Earth. Ultimately, the way we approach Mars will set a precedent for how we interact with other worlds in the future. If we find life, how we respond will reflect our values as a species. Will we prioritize expansion and exploration, or will we recognize that Mars, and any life it may harbor, has a right to exist on its own terms? These are not just scientific questions, but philosophical ones, forcing us to confront our place in the universe and our responsibilities as stewards of life, whether on Earth or beyond. The search for life on Mars is far from over. In fact, some of the most exciting discoveries may still be ahead of us. One of the most ambitious and highly anticipated projects in Martian exploration is the Mars Sample Return (MSR) mission, a collaborative effort between NASA and the European Space Agency. While rovers like Curiosity and Perseverance have provided invaluable data, nothing compares to the power of analyzing Martian soil and rock samples in the sophisticated laboratories on Earth. These samples, carefully collected and sealed by Perseverance, will be retrieved by future missions and sent back to Earth, where scientists can examine them for definitive signs of past or present life. If biosignatures exist in Martian rocks, the MSR mission could provide the strongest evidence yet that Mars was once a living world. Beyond sample return, the next generation of exploration technologies promises to push the boundaries of what we can discover. Future rovers will be equipped with even more advanced instruments, capable of detecting subtle chemical and biological signatures with greater precision. Subsurface exploration is also a key focus, as scientists believe that if life exists today, it is most likely hidden beneath the surface, where it would be shielded from radiation and extreme temperature swings. Upcoming missions could include deep drilling systems that penetrate meters below the surface, reaching potential underground water reservoirs. Radar technology, already in use by orbiters, will continue to improve, allowing scientists to map buried ice deposits and potential liquid water lakes. Another breakthrough in Martian exploration is the introduction of aerial vehicles, like drones and helicopters, which provide access to previously unreachable terrain. NASA's Ingenuity helicopter, initially a small experiment, proved that powered flight on Mars is possible. Future aerial explorers could scout for promising landing sites, assist rovers in navigating rough landscapes, and even conduct independent scientific missions, dramatically expanding our ability to explore the Red Planet. Perhaps the most ambitious goal of all is sending humans to Mars. While robotic missions continue to make incredible discoveries, human explorers would bring adaptability and decision-making skills that no machine can match. Space agencies, including NASA and SpaceX, are actively working on plans to land humans on Mars within the next few decades. A human presence would allow for real-time scientific exploration, rapid sample collection, and even the construction of long-term habitats. However, the challenges of such a mission are immense, from ensuring astronauts' safety during the long journey to developing sustainable life support systems and protection from radiation. Despite these challenges, the dream of setting foot on Mars is closer than ever. Whether through robotic missions or human exploration, the coming decades promise to be a defining era in our search for life on the Red Planet. If we do find evidence that Mars once hosted or still harbors life, it would be one of the most Profound discoveries in history, changing our understanding of biology, evolution, and our place in the cosmos. The search continues, and the answers may be closer than we ever imagined. The search for life on Mars isn't just for scientists and space agencies. You can be a part of this journey too. Thanks to modern technology and the rise of citizens science projects, anyone with an internet connection can contribute to real scientific research. Organizations like NASA and the European Space Agency, ESA, regularly release images and data from Mars missions, allowing the public to help analyze them. Through projects like Planet 4 and AI for Mars, volunteers assist in identifying surface features, mapping terrain, and even training artificial intelligence to help rovers navigate the Martian landscape. By participating, you're not just observing space exploration, you're actively contributing to it. Beyond direct involvement in data analysis, there are many ways to engage with astrobiology research and stay connected to the latest discoveries. Universities and research institutions often host online courses, webinars, and outreach programs that allow the public to learn more about the science behind planetary exploration. Even discussing the search for life on Mars, sharing findings on social media, or engaging in science forums helps build awareness and excitement around these groundbreaking missions. Another way to stay involved is by following space agencies like NASA, ESA, and private companies like SpaceX, which regularly provide updates on Mars missions. Live broadcasts of rover landings, mission briefings, and Q&A sessions with scientists give an inside look at the incredible work being done. Subscribing to mission updates, following space agencies on social media, and watching live streams of launches and discoveries help bring you closer to the action. Finally, one of the most important things you can do is to stay informed and keep the conversation going. New discoveries about Mars and the possibility of extraterrestrial life are happening all the time. As technology advances and future missions push the boundaries of exploration, we may be on the verge of answering one of humanity's greatest questions. Are we alone? By staying engaged, supporting space exploration, and inspiring curiosity in others, you help drive the momentum that could one day lead to the most profound discovery of all, the confirmation of life beyond Earth. The search for life on Mars is one of the most profound scientific quests of our time. It is a journey that goes beyond curiosity. It touches the very heart of our understanding of life itself. If Mars once harbored life, even in the form of ancient microbes, it would prove that life is not unique to Earth, and that the universe may be teeming with biological possibilities. If we discover that Mars is sterile, it will still teach us valuable lessons about planetary evolution, habitability, and the delicate conditions that allow life to flourish. Either way, the search brings us closer to answering the age-old question: are we alone? What makes this journey so exciting is that we are still in the early stages. With every mission, every new set of data, and every groundbreaking discovery, we refine our understanding of Mars and its potential to support life. From the Viking landers to the Perseverance rover, each step has built upon the last, bringing us closer to unraveling Mars' deepest secrets. Future missions, including the Mars sample return and eventual human exploration, will push the boundaries even further, providing unprecedented opportunities to study the planet in ways never before possible. As we look to the future, there is every reason to be hopeful. The coming decades promise to be a golden age of planetary exploration, with advancements in technology opening new doors to discovery. Perhaps the next major breakthrough, the one that finally confirms life beyond Earth, will happen in our lifetime. Whether you're a scientist, a student, or simply someone fascinated by the cosmos, you are part of this journey. The search for life on Mars is not just about exploring another planet. It's about understanding our place in the universe. So, as we continue to push the boundaries of discovery, one thing is certain: the adventure is far from over.